Thank you. Great. So can you hear me okay? Cool. So first, thank you to the organizers for putting together this, this nice school and the subsequent workshop. It's great to be here. This is actually my first time in Korea, so I'm excited to just kind of see this country. But today, I've been tasked, I think, to offer you a kind of introduction to scattering amplitudes, kind of connecting to what we saw in the previous lecture, working from the ground up. My impression is that the kind of audience is not by any means experts in scattering, but maybe has a varied background in kind of particle physics, phenomenology, and maybe some kind of formal aspects of QFT. So I'm going to try to play kind of to that audience. A lot of what I'll tell you about in this first lecture is really about, well, in large part about the motivations for why, at least I personally am interested in scattering amplitudes. So when we go to these conferences on scattering, there's a really broad spectrum of people from very different kind of sub-disciplines of physics. So of course, there's particle physicists and there's string theorists who are interested in scattering. But as of late, there's been a uptick in kind of other groups, which include gravitational wave physicists and mathematicians and cosmologists. So part of that reflects a feature of scattering amplitudes, which is it's a very broad kind of outlook on how to approach problems, where the basic essence is rather than to start with, say, a Lagrangian or a Hamiltonian or a set of equations of motion, the kind of usual way we think about things, we instead attempt to bootstrap directly to the final answer. So if you could summarize, or if I could summarize in like kind of one little diagram what the S-matrix program is about, the idea is that instead of the action, okay, so we're used to thinking about, let's say, an action in some d-dimensional space-time of a Lagrangian, probably, like most physicists, 90% of your time is about thinking about this Lagrangian, its symmetries, its particle content, and so on and so forth. We would think of this as kind of the kind of gold standard of knowing what a theory is. And as an afterthought, we might compute something like the S-matrix if we want to compare to experiment in order to get cross-sections to then verify whether our theories are correct. The S-matrix is one observable. There's other observables where some of the ideas I'll tell you about also apply, like correlation functions, well, really correlators in anti-de Sitter space or de Sitter space. But there's a whole we usually think of the S-matrix and those things as a byproduct to check the answer. Now, as you, I'm sure, are well aware, I don't have to say it too explicitly, this picture is a little misleading because really we don't start with the action. We start with a set of physics principles. So a set of principles that are up to you, that we assume, which we then build into an action. An action depends on symmetries, which we assume or infer based on experiments. And the action is not the thing we start with. We start with some set of more underlying tenets. From this point of view, when we talk about measuring things in experiments, those measured quantities, like let's say masses and Yukawa couplings and gauge couplings, the fact that they can take on freely different values is precisely the statement that they are not fixed by principles. Okay, so principles like Lorentz invariance, unitarity, or the symmetries of your theory, all those things do not fix parameters we can measure in an experiment, which is why they can take on many values, and we're forced to measure them, and that's our only recourse to extracting that last piece of data. So that's really ultimately the picture of how we do physics, which is we start with principles, derive an action, and then compute the S-matrix. This whole program of the bootstrap, which which UT nicely introduced, essentially starts directly from the principles and then sculpts out the S matrix from it. Okay? The idea, it may sound kind of crazy that you can do this, but the way it works quite explicitly is you think about what kinematic variables your observable depends on. So for the S matrix, this would be, let's say, Mandelstam invariance or momenta. And then you write down a function, an ansatz, which flexibly parameterizes the space of possible S matrices. Now, of course, if you assume nothing and you're just left with an arbitrary function, it's not very useful. What you assume needs to be sufficiently constraining to input your principles. We'll talk deeply about what we need to assume and what we can get from it. But once you have that ansatz, you then assume things. Okay, so you assume symmetry or more symmetry or this property or that property, but all framed within the statement of physical principles. Okay, and then what you are left with is some function of some number of parameters, and that is your putative S matrix. Okay. Now, there is kind of two paths to this picture. In one path, you kind of reproduce things you already know. That's what I'll do for maybe the first part of my lectures, which is kind of reinvent the wheel, so to speak, by taking this roundabout procedure and deriving things like gauge theory and gravity without the usual tools or crutch of notions like gauge symmetry or diffeomorphism invariance and so on. Okay, so there's a certain very Lagrangian-centric quantum field theory-centric description which we can avoid entirely in order to derive those theories. And the win there is that we learned that those theories are not, if you like, they're unique in a very rigid sense. We don't just study Yang-Mills theory because some smart person wrote down the Lagrangian. We write it down because any minute or continuous deformation of it is usually excluded for reasons that are dictated by the principles we'll state. Okay? So that's one angle, which is reinventing things we know. That'll hopefully be not too much of what I'll talk about. But after we kind of get lift off on that kind of bootstrap picture, I then want to tell you about things we can genuinely learn that are new by looking at it through this picture. In other words, by skipping the action and going directly to the S matrix. That kind of second part of this talk, I'm going to call hidden structure, which is kind of a vague terminology. But what it basically reflects is that the theories that we talk about that comprise the standard model, like non-abelian gauge theories, gravity, the chiral Lagrangian, QCD, all these theories, we think of them as linked together by the laws of nature that we observe. But as actual theories themselves, they're connected. They're linked and connected in ways that are kind of universal and, in my view, still quite mysterious. Okay? And this will relate to something called the double copy, or called the kinematics duality, and other kinds of like ways of linking theories. And I'll mention that maybe towards the latter part of those lectures. Okay, now before I kind of maybe dive into the mechanics, I did want to motivate why you might ever expect to learn about new structure from an amplitude just by staring at it. And I want to kind of present to you the kind of canonical, I think I'm almost required by law to show you this, avatar for why scattering amplitudes are much simpler just in the expressions than you would have naively expected given what you learned in your textbook quantum field theory courses. Okay. So to show you this, let me talk about a very concrete here. Okay. So, and apologies if you've seen this analogy maybe once, twice, or many times. But in Yang-Mills theory, we can think about the kind of next to simplest process, which is not 2 to 2, but 2 to 3, gluon scattering. Okay, so imagine tree-level gluon scattering in Yang-Mills theory. Of course, you know how to compute that from your textbook Feynman diagrams. And what you would get is some expression which involves things like polarizations and momenta. So you'd have terms, let's say, that look like, let's say polarization E1 dot E5. This is just an example. You don't have to write this down. I'm just illustrating the types of expressions you get. Inner products of momenta and polarizations. written in some, just picking out a term here, on the upstairs with denominators that involve propagator functions from Feynman propagators, plus dot, 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 where dot, dot, dot here is like hundreds of terms. Okay, so if you just computed using the classic methods of Feynman diagrams, given the Yang-Mills action, this is what you get, and this is a lot of terms, hundreds. And if you didn't know better, you just stop there and say, this is the answer. Physics at the Lagrangian level is beautiful. Physics at the level of what we observe in experiments is ugly, and then you'd stop. Okay, of course, this is not, this is actually very misleading. Okay? It's very misleading because when I write an expression like this, I've actually written down, if you like, an off-shell expression, because usually when we do this, we don't enforce necessarily on-shell conditions like momentum conservation or the fact that p1 squared, p2 squared, p3 squared, p4 squared, and p5 squared are 0. Okay, those are constraints that reduce the size of this, this expression. But it turns out that this is a much more complicated way of writing a simpler, well, the answer, which actually, if we talk about physical states, is incredibly simple. Okay, so by physical states, I'm going to introduce notation I'll use throughout. We have to talk about external gluons that are polarized, either to be plus or minus, left or right circularly polarized. There are 2 helicities to the gluon in 4 dimensions. So it doesn't make sense to just talk about them in terms of polarizations. So really, we should talk about 5 gluons, which have some set of polarizations, which I'll choose and define to be in all-in convention. Okay, so these are 5 minus helicity gluons coming in. Okay. What this would mean is plugging in very particular choices for these polarizations. As it turns out, famously, this, if I go to on-shell kinematics asking about a physical process, for all minus, this is 0. Okay? In other words, this hundreds of term expression is nothing more than a very complicated rewriting of 0. The same is true if we add 1 plus, 2 minus, 3 minus, 4 minus, 5 plus. This is also 0. Okay? So we're starting to think, oh, is this somehow trivial? But no, we actually end up, once we reach the sector with 2 pluses and some number of minuses, or 2 minuses and some number of pluses, a non-zero answer. Just write this for the case of 5-point, where I'm going to introduce for the first time, maybe for some of you, but maybe not all of you. Okay, a certain angle bracket notation, which is called spinor helicity formalism. Okay, so I'm going to talk about this in great detail shortly, but the point of spinor helicity is it's a rewriting of the usual P1, P2, P3, P4 kinematic data in terms of spinors whose dot products are precisely these angle brackets. Okay, I will unpack what they are, where they come from, why this is the expression, but in this motivating story in the beginning, I just want to emphasize to you that this is incredibly simple. It is a monomial expression, far simpler than the hundreds of terms here. Okay, so this is often cited as a kind of Park-Taylor miracle. This is something that was observed by Park and Taylor in the 70s, which was this realization that what we compute is massively more complicated than the actual answer, which is this. Now, this immediately suggests that there's a better way to compute, which isn't through Feynman diagrams, which directly spits out this object, right? As physicists, when we see a beautiful final expression, after simplifying, we think, well, there must be a more direct geodesic path to this, and we want to know what that is. And in fact, by studying the expression itself, we can actually learn more about the theory. Okay, so here I want to mention something which is connected to very topical physics that is of interest, I think, very much in HepTH today, which connects directly to this amplitude, which I should maybe just in terms of terminology, I'll say this is called the maximally helicity violating amplitude. I'm not going to write it out, but MHV, maximally helicity violating, okay, for historical reasons. All it means is this amplitude with 2 minuses and the rest plus. It's the first amplitude that isn't 0 at tree level in this theory. This MHV amplitude, as soon as this formula was written down, in fact, it was written down at endpoint, and it was similarly simple, people realized that it had some kind of structure. You can already see it. Not only is it simple, it has this cyclic structure of angle brackets multiplying each other. Shortly after the original papers, VP Nair realized that this looks precisely like a correlation function in a two-dimensional CFT, a WZW model. Okay, just reasons I won't get into, but each of these factors looks like the factors you get from taking an OPE in a 2D CFT. And that was a very interesting observation that I think today has kind of transmuted into what is essentially the celestial holography program. So if you've heard of this, this is a very ambitious program that attempts to take flat space, four-dimensional scattering amplitudes, and reinterpret them holographically as correlators on the sky. Okay, so what you do is you think of the angles in the sky as a two-dimensional manifold on which a conformal field theory lives, and you try to interpret these as the correlators. Again, this is research in progress in the sense that they have, I think, yet to, I'd say, fully successfully build a holographic dual, but all those structures are just here, sitting in the amplitude for you to see. Another place where this, by looking at this, we learned about structure within Yang-Mills is a famous paper from 2003 by Ed Witten, who showed how MHV amplitudes look like certain curves in twistor space relating to the so-called topological string theory. Again, basically giving another dual picture for how to compute Yang-Mills amplitudes. Okay, so the upshot here is that by studying these amplitudes directly, which are extremely simple, we can, in post, try to determine structure from them. Okay? And that's how we can actually learn about hidden structure directly from the amplitude. And so this is not like an abstraction. This literally has happened and is the kind of backbone of a number of research programs nowadays. Now, this statement I made about gluons is super good. It's a question. Yes?
Why do amplitudes are zero? Is there any interpretation?
Yes. So fundamentally, these kinds of vanishing, you can understand much more kind of in a pedestrian way by, well, there's a couple ways. Let's say at a calculational level, if you computed the Feynman diagram expression and had polarizations, you can very wisely and cleverly plug in the polarizations in a way that makes this zero manifest, actually. Simply because if you choose your polarization references wisely, you can get inner products to vanish trivially. At a physical level, so that's like the technical level, how you'd see from a Feynman diagram expression something like this vanishes. At a physical level, we would think about something like factorization. Okay, so that will take, maybe if you wait a couple more minutes, we'll get deeply into how that works. But in many cases, at tree level, there can only be certain things exchanged. Even if you study the Feynman vertices in Yang-Mills theory, you only have quartic and cubic vertices. You could simply ask which types of helicities can be conveyed through those channels, and you could also make arguments like that. But I'll actually unpack that a bit more later. So if you can hold that thought, we'll go through that carefully. Any other questions? This is great. Actually, the more questions you ask, the better, because then I won't fall asleep, and you also won't fall asleep. Good. So everything I said here was about Yang-Mills theory, gluons, but it's also true very generally. Let me give you one more example. I will talk about not just gauge theory, but also gravity. Okay, so this was the case of, let's say, the Yang-Mills 5-point function. We can also talk about the scattering amplitudes in gravity, which are called amplitudes in general relativity. This will come into play, I think, a lot in later lectures by others who you're lucky to hear from about applications of scattering amplitudes to gravitational wave physics. Okay. Now, you might, if you're kind of uninitiated, this may seem confusing. What do I mean by scattering in gravity? Well, I quite explicitly mean the scattering of gravitons in a flat background. Okay, so by this I really mean, this is a parenthetical, the action root G R, where we take G mu nu and we expand in flat space, eta mu nu plus H mu nu divided by M Planck. Okay. So we think of some degree of freedom called the graviton. When we expand by plugging in this into the Ricci scalar, we get a whole bunch of very complicated terms, and we can compute the endpoint scattering amplitudes in that theory. Okay. You can think of it as these are the scattering amplitudes for weak field plane waves interacting through Einstein's general relativity. Computing these types of amplitudes has been crucial for the connection between amplitudes in gravitational wave physics, of course. This is the kind of the link between those two separate topics. But I'm mentioning it because we can also, in the same way that we could ask about the Yang-Mills amplitude, we can ask about the graviton amplitude. Okay, so this is something which I won't write on the board, because if you use Feynman diagrams for this, they're very complicated. As you can anticipate, much like in the chiral Lagrangian, this action has more and more high powers of h squared, h cubed, h to the fourth, h to the fifth, has more and more complicated vertices, and has spin 2, so it's quite messy. This expression for the amplitude, if you compute with Feynman diagrams, is roughly 100 kilobytes. Okay? So I won't write it down. You just have to store it in a computer, and you could say, oh, that's physics. It's just ugly. But here again, as it turns out, if I fix this to have helicities, let's say minus, minus, plus, 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 plus. Okay? So here I'm putting two minuses and two pluses because the graviton is spin 2. So this is helicity minus 2, helicity minus 2, helicity plus 2, helicity plus 2. Okay? When you actually restrict to physical configurations, what you find beautifully is that this thing is extremely simple. Arguably as simple as that expression, b4 to the fourth over STU. Okay, so STU are the usual Mandelstams. In other words, that 100 kilobytes of just stuff compactifies again into a very simple expression. Okay. We will also derive this through kind of first principles logic a bit later. Okay, so the point is gravity, which doesn't have a gauge symmetry in the strict sense, but has a diffeomorphism symmetry, also has a huge redundancy in that the Feynman diagrams are way more complicated than the final answer. I should maybe also mention that just like in the Yang-Mills case, there's a beautiful MHV formula for all amplitudes with two minuses at endpoint. There's also an analogous formula in gravity with two minus helicity gluons for endpoint also. So we have these general formulas that are extremely powerful and suggest some deeper structure. Okay. Any questions about that? Good. Now, all of this might suggest to you that this is some very special property of, let's say, gauge symmetry and gravity, which have redundancies because gauge symmetry isn't a real symmetry. Gauge symmetry is a redundancy of description in the way we choose to describe things. Of course, we know that. That's why we fix a gauge when we compute. That's also why your gauge never affects your answer. If your gauge affects your answer, you did the calculation wrong. So it's always in the back and is a property of our kind of way we think about the physics, but it's not in the observables, of course. So for this reason, you'd think maybe gravity and gauge theory are unique. But I want to tell you one more example which I find instructive, which is a scalar field theory that's also redundant. Because this redundancy is universal. Okay, so if you only cared about the Higgs boson or pions, you might think you're safe because there's no redundancy. It's just a scalar. But nevertheless, there is still a huge redundancy even when we talk about scalars. So let me illustrate that in a particular example that I like to talk about and which we'll actually return to, which is the following. Okay. Consider the following Lagrangian for a scalar field, a single real scalar field, okay, where g of phi is some arbitrary function of phi, which is has a regular expansion at the origin. So g phi equals 1 plus lambda 1 phi plus lambda 2 over 2 phi squared, and so on. Okay, so it's just a series expansion about the origin. Okay, this is a theory that you might think of as some effective field theory I write down with essentially many derivative interactions that go to arbitrarily high order. Okay? But I want to emphasize crucially that this thing has no, I'm not assuming anything special about lambda 1, lambda 2, and lambda 3. It's just totally arbitrary. Okay? So we would describe this in Lagrangian language as a two-derivative theory of a scalar. That's what this would be. And as you can see, I'm writing a Lagrangian not because we're going to need it actually, but because for purposes of being instructive, I'm going to frequently flip between the amplitudes picture and the Lagrangian picture to just make sure you understand that nothing is mystical. There's no magic happening. Everything we do on one side has an avatar on the other side. There's no free lunch. Everything that's unique is unique for a reason. But it'll be nice to just see mechanically how the Lagrangian and the amplitudes perspective mixes up. Now, why am I bringing up this theory? Well, but the kind of one of my points here was that just because you have a Lagrangian that looks like it has lots of rich interactions at 3, 4, 5, 6 point, you might think, okay, this is just some very complicated, probably not even renormalizable theory, right? It looks like it's got a lot of derivatives in it. Surely this thing must have some, random S matrix. But, well, let's see. Okay, so let's compute. So let's say we computed A3, the 3-particle scattering amplitude. So what that just means is, this single vertex, we're going to do this at tree level. Okay. What do we get? Well, we get minus lambda 1 times the Feynman vertex, which is just P1.P2 summed over permutations, P1.P2 plus P2.P3 plus P3.P1. Okay. This is just the Feynman rule, which we can now actually rewrite as P1 squared plus P2 squared plus P3 squared. Why can we rewrite it that way? Well, we can rewrite it that way because P1 plus P2 equals minus P3. Okay, so this is crucially where things like on-shell matter. Momentum conservation will matter for every statement I'm going to make, and so will the on-shell condition. So if I take momentum conservation and I square it, I have P1 plus P2 squared equals P3 squared. Okay. You can see that I'll get a cross term, P1.P2. P1.P2 will be an equation with P1 squared, P2 squared, P3 squared. So I can replace every dot product between Pi and Pj for I not equal to j with just P1 squared, P2 squared, or P3 squared. So you do that and you get this expression. But this is 0 because P1 squared and P2 squared and P3 squared are all 0 by the on-shell condition. Okay, so in other words, this 3-point amplitude is vanishing. It's 0. So you might conclude at that point, okay, that's maybe not too shocking. 3-point is weird. It's a strange kinematic configuration. That's fine. We'll look at 4-point and compute something and get something reasonable. But, well, let's see what happens. So let's say we compute the 4-point amplitude in this theory. So the 4-point amplitude, it's a similar type of calculation, of course. Again, just using Feynman diagrams, nothing special. So we have terms, let me write them out. S plus T plus U minus lambda 2, S plus T plus U. Okay, so these terms here come from just the contact quartic. So there's a 4-point function for phi, which is here. That's what this term is. While these terms here are the S, T, and U channel Feynman diagrams. Okay, so these are just usual Feynman. Now, as you can see, everything is proportional to S plus T plus U, which is 0, again, for these massless particles. So 4-point's also 0. In other words, the 4-particle amplitude is also vanishing on shell, 3-point and 4-point. Okay. If you keep marching up, you'll discover 5-point is 0, 6-point 0, every endpoint is 0. Okay. All the amplitudes in this theory vanish. Okay. Now, I'm not claiming that every theory has this property, but this theory, the Lagrangian with 2 derivatives for one real scalar, has vanishing tree amplitudes. If you chose to include loops and compute, you'd still find 0. Is 0, 0, 0. Now, this would seem mysterious if you thought the Lagrangian told you everything you had to know. You'd say, this has interactions. What's going on? What's the magic step? Well, the magic, the thing that got lost in translation here is that this is secretly equivalent to a completely free theorem. In fact, let me continue that statement here. Okay. So there is an operation that we'll talk about kind of off and on called a field redefinition, which is something you might even find familiar with if you've worked at all on phenomenology with respect to effective field theories. So in effective field theories, for instance, the chiral Lagrangian for pions, the standard model EFT. So there's maybe some interest more recently in thinking about the standard model plus higher dimension operator corrections and how colliders can constrain them. There is a famous kind of redundancy in the very operators that show up in those theories, which is linked to what's called the redundancy of field redefinitions. And it basically is the following. Okay, so this is the statement. If you take a field theory and you redefine the field, phi goes to phi plus f of phi, where f prime of 0 is 1. Okay, so that's just another way of saying, so in other words, just another way of saying phi goes to phi plus nonlinear in phi terms. This is nonlinear in phi. So phi squared, phi cubed, and so on. Okay. This procedure leaves on-shell S matrix amplitudes completely invariant. Okay. So it sounds crazy if you haven't seen this before, but this statement here is not that this is an invariance of this action. If you do this, your action changes. In fact, the point of this is that I can choose an F. I can choose an F such that this maps to a free action. That's actually the cheap and fast way to discover that this is a totally trivial theory, which is I can do a field redefinition to map this to a theory with no interactions. Okay. Why are you allowed to do this? Well, it boils down to the fact that in quantum field theory, fields are actually auxiliary. There is a path integral, right? When we do a path integral, our whole purpose is to write down a field and integrate over all of its configurations, right? In fact, when we write down, let's say, a partition, when we write a, oh, wow, okay. Let's do that. When we write down a, oh, okay, cool. When we write down a path integral, the whole point is we'd say, for instance, z functional j equals some path integral over d phi e to the minus s phi plus j phi, let's say. Okay. We'd add some source and then integrate over phi. Okay. But phi is an integration variable, so we can change variables. And the answer will transform, the integral transforms. But as long as we're careful with what our sources are, we can transform from one coordinate to another. One way of thinking about this transformation is it's just like going from Cartesian to polar. Okay? When you go from Cartesian to polar coordinates, your Lagrangian is not invariant. It changes. It literally is different. But no one's worried that your scattering angle or your binding energies will change. Those physical quantities, in particular the ones measured in infinity, are invariant under that transformation. Okay? So this is a huge redundancy when we write down an action. When someone hands you an action, you can do any transformation of this type, and it will leave all these S matrix elements invariant. Now, it doesn't leave correlators invariant. Okay? So for instance, if you were computing non-Gaussianities in the early universe, you would care about the difference between phi and f of phi. But of course, you just replace phi with f of phi. So it's, if you like, covariant under field redefinitions, not invariant, but still in a way that we can handle things. Okay? But the basic point is it doesn't matter the coordinates that you compute with. You should be able to use any of them. And as long as you map them properly onto your experiment, you will get the same answer. Here we've witnessed an explicit sense in which there is a redundancy. These two Lagrangians look different, but describe precisely the same physics. What that means is that there's a huge redundancy just in Lagrangians. So if I gave you, let's say, okay, a Lagrangian for Yang-Mills theory from Peskin and Schroeder, I can do a field redefinition to it. Or let's say I take a change of gauge to transform it to another Lagrangian, L2, and to L3 and L4 and so on. I can generate an infinite number of equivalent Lagrangians, all that have the same physics, but which all map to precisely the same S matrix. Right? So there's no distinction between them. The fact this huge many-to-one mapping is a redundancy. Part of that redundancy we saw for Yang-Mills. Okay? The redundancy of choosing a gauge, of the way to write your propagator, what's a gauge fix. All those redundancies are what made the Feynman diagram picture cumbersome. But if instead we ignore the Lagrangian, we cross them out, and we just go directly to the S matrix, we mod out, we eliminate all of that redundancy, and we can just stare at the answer. Okay? So this is one of the beauties of this program, is that the actual expressions we look at are maximally simple because they're gauge invariant and field basis invariant most of the time. Okay? We're dealing with correlators, it's more complicated, but this is an immense advantage. Any questions about that? Okay, let me mention one thing because it's just kind of fun. It has to do with this Park-Taylor simplification. And also because I think at some point this conference had AI in it, which is that this procedure of taking an incredibly complicated formula and compactifying it down to like one term is something which seems maybe tailor-made for a kind of machine learning type problem, because it's very complicated. A single human would take many days to simplify 6-point to lower point. But if you could train something to learn how to do it, it would be much faster. So one thing I'll mention is a current project, which we should be wrapping up in print soon, is a machine learning algorithm that takes huge spinor helicity expressions and simplifies them. So what can it do is actually eat the 200-term Park-Taylor formula at 5-point. I'm sorry, 200-term Feynman diagram expression at 5-point, and just spit out the Park-Taylor form. And it does so in a way that is remarkably unguided, which I could tell you about offline. But this is something which we may actually end up releasing because it seems kind of useful. You could plug in graviton amplitudes and have them simplify to give you new expressions for these well-known formulas, well-known but complicated Feynman diagram expressions. Okay, good. Any questions before I move on to more technical substance? I think hopefully I've been able to convey that there's huge redundancy in the way we do things. Let's remove that redundancy and ask about what the theories actually are telling us. Okay, I could. Let me, again, maybe just because this is an introductory talk, let me just mention the kind of various outgrowths from amplitudes, just because they may have different, the audience may have different inclinations and things they connect with. I'll just mention this here. I would say that amplitudes has kind of two rough categories of results in recent years. One of them I would call kind of hidden structures, or structures where basically we're looking at Yang-Mills or gravity. They've been studied for decades, century, more than a century in some cases. But we're learning about structures and new ways to formulate those theories and new connections between them. So this is kind of a formal hep-TH angle. And then there's the other angle, which is kind of raw applications, which is like, what can I use this for? What is this good for? Okay. In terms of applications, there's always been collider physics. This is the kind of the tried and true origin of many of these ideas, which kind of gave much of this program its kind of technical oomph. Things like integration by parts and generalized unitarity. These kinds of ideas were, if you like, invented in many cases practically just to compute to high orders relevant to collider physics. Another, maybe put applications in quotes, is calculations in supergravity, which are not, of course, for an experiment, but if you like, or is about going to very high orders and asking about when gravitational loop integrands are more convergent than you would have assumed. Okay, so it's kind of seeking structure, but it's an application of many of these ideas. Here, let me mention kind of the more topical subjects, which I really won't dive much into, but others will. Gravitational wave physics. This is something that in the last, I think, less than 5 years, it was realized that we can take the tools that I'll mention some of the tools I'll mention and others, and reappropriate them to think about the binary dynamics of black holes. Okay, so that may seem drastically different physics. How could this be connected? This guy's talking about gravitons, now he's talking about black holes. But for reasons that you'll see when Josh Shen talks about this and others, you'll see that there's a super direct connection, and incredibly, the state-of-the-art calculations in what's called post-Minkowskian expansion, which is just the G Newton expansion, are now done in amplitudes. Okay, so the folks who do these are amplitudes people, no longer the ones who were kind of originally the gravitation wave theorists. The ideas are all kind of mixed up, but I think real progress has happened there. That's a story I will maybe touch on, but not a lot. There's also cosmological correlation functions. So this is kind of applying the ideas from amplitudes to correlators in cosmology. And maybe last thing I'll say is positivity bounds, which Yutin nicely introduced. And again, I call it an application because it's about sculpting out the possible worlds of Wilson coefficients that are consistent with general principles. Okay? And we should care about that because we're going to measure those Wilson coefficients, or at least bound them in colliders, and they're relevant to sensitive experiments. That's the kind of application side. For the structure side, there's other, I would say, just kind of more formal questions, some of which I'll touch on. One of which is the double copy, so-called color kinematics duality, or BCJ. You'll hear, I'm sure, some nice lectures from Henrik, who is one of the discoverers of this certain flavor of this structure, which, if I were to say in short, what it says is that gravity is kind of composite in a deep theoretical sense. It is comprised of two copies of Yang-Mills theory, and that this little cheat code lets you compute in gravity much more easily by computing in Yang-Mills first, and then essentially squaring the answers in a precise way. So this is something which, at least to me, is still very mysterious from an origin, in terms of quantum field theory. There's a lot of people thinking about this kind of idea, but I will talk about this. Other topics I won't talk about, but you've probably heard about, are, I'm going to call this polyhedra, or amplituhedra, or associahedra. So if you've heard about the amplituhedron or the associahedron, anything kind of coming from Nima Arkani Hamed's camp, the idea is linked. I mean, there's a huge constellation of mathematical ideas and physics ideas, but their kind of common feature is that it aims to rewrite scattering amplitudes and the S matrix as volumes or natural geometric objects in a completely different space, in a space that isn't space-time, that is written in an entirely different way. But in doing so, things like unitarity and Lorentz invariance maybe would even emerge more dynamically. Okay? So that's the kind of overarching bullet point I'd say for those. Again, I won't say very much about that. Okay, there's the list goes on. I mentioned celestial holography. There's twisters and so on and so forth. There's a long kind of list of kind of more formal aspects, which I'll touch upon here and there. But I wanted to give you kind of a lay of the land. There's this bifurcation between kind of hyper practical, let's get to the next order, for those who want to actually be able to compute something that would be relevant to the world definitively that we live in. And there's statements that are about the consistency of what the world could be or not. I should say also, this positivity statement, you also hear more about, not just in terms of constraining Wilson coefficients, but in terms of determining whether things like string theory or other well-studied theories are truly unique in the sense of them being consistent with low energy principles. Okay? And that again is something which has, I think, had some progress recently, basically trying to bootstrap strings. Like if you didn't have Polchinski's volume 1 and 2, and all you had to work with was the Veneziano amplitude and that kind of picture, how much of string theory could you derive from a bottom-up point of view? So that's what I would say is my own biased view of maybe some of the interesting features that have occurred and also some structures, and I'll touch on all of these in some deeply, in some cases less deeply. Okay, good. Any questions before I move on? Yes?
now I think that you have introduced a lot of authentic amplitude method compared to the Lagrange language.
Yes.
Yeah, so my stupid question is, if we address the amplitude method sequentially, then finally we will with the error where we don't need to use the Lagrange language.
I think that's not a stupid question. I think like that's a reasonable possible outcome, but I'm way less of a zealot to advocate that that will ever happen. So I'm, as folks who know me know, I have no principles whatsoever. And what that means is, if you, in my view, if you discover a structure like celestial correlators or the double copy, it's possible that purely studying amplitudes and going to higher loop order will demystify and give you all the conceptual earnings that you could ever imagine. But at least for me, I think you can go back and use QFT to try to understand all of them. So in fact, I'm going to commit to that. I think when I talk about the double copy, I'm going to introduce it as it should be introduced from an amplitudes point of view, but then I will give you a quantum field theory explanation for at least some of these double copy structures. So at least for me, this is just the way I think about things. It's not either or. I don't think we need to jettison anything. We should totally, in an unprincipled way, use whatever tool we want, whenever we want, to solve whatever problem we want to solve. So I would say, I know others would say, yes, Lagrangians, we should never use them, but they don't use Lagrangians anyway. So they don't. so I'm just saying, I'm not that much of a zealot. Personally, I think you should just use whatever tool your friends don't know to solve a problem. That's your main advantage. Yeah. That's a reasonable question. Any other questions? Okay, good. So if there are no more questions, let's actually get to something a little more meaty. So again, this is the first lecture, so I need to tell you what my assumptions are for a very basic bootstrap. Okay, so let me just start here. Okay, so what's the plan here? So the plan here is I'm going to kind of illustrate the way that we think about bootstrapping an amplitude without a Lagrangian. Like, how do we even do that? What's the picture for the mechanics for how to do that? And then hopefully as fast as I can get to more interesting structures that are less intuitive. Okay. So, but first I have to start with this more responsible stuff, which is the physical principles. Okay, so which principles are we going to assume? Okay, so what do I assume? So I'll just go through these in turn. So it seems maybe too minor to say, but dimensional analysis is actually so surprisingly crucial and important in this business, more so than it usually always is. What do I mean by that? Well, let me just be explicit. So let's say I talked about an n-particle scattering amplitude. Okay, so what do I mean by this? I mean, take an n-particle correlator, amputate its legs, do LSC to it, you get some object, and then strip off that delta function. That's what I'm going to call the amplitude, AN. It has some fixed mass dimension, which in general D is capital D plus N minus Dn over 2, okay, which in D equals to 4 is 4 minus N. Okay, usually something we wouldn't bother specifying, but I am specifying it for the following reason. If you compute an amplitude, mass dimension enters in two ways. Okay? The first way is through kinematics, momenta, P, P1, P2, P3, P4. The second way is through coupling constants. Okay? And since we don't have a Lagrangian to start with, we're not assuming anything about the Lagrangian, we have to be careful about the dimensionality of those. And they're kind of complementary in the following sense. So, okay, I'm just going to make an obvious statement that let's say I was in a gauge theory and I had some fine structure constant. This would have mass dimension 4 minus D, which in D minus D equals to 4 is 0. Or I could think about gravity in D dimensions. So this is G Newton. This would be 2 minus D, which in D minus 4 is mass dimension minus 2. Okay. But my point here is that when we write down these ansatzes, we have to kind of in the back of our minds recall that there's a coupling constant. Okay? So there's kind of two ways that we can think about building an ansatz. One way is to say, I want to build an amplitude that has this many powers of p, like 6 powers of p. Now, as soon as we demand that that amplitude has 6 powers of p, like p to the 6th, because the amplitude has fixed dimension, it then fixes the dimensionality of the coupling, okay? And vice versa. So if instead I said, I want to write down something with dimensionless coefficients, alpha, then alpha would be dimensionless, and that means all the number of momenta have to constitute this mass dimension. Okay, so stating the mass dimension and stating the coupling dimension are kind of complementary to each other. Depending on what your bootstrap is, you will impose, fix one or fix the other. Okay, that's pretty clear, but I thought I'd say it because we'll actually do that a fair amount. Okay, second assumption, called this exchange symmetry. And by this, I just mean Bose symmetry or fermion, Bose or Fermi statistics. So all this means, I'm not going to write out the words, is if we take two identical bosons and we swap them, okay, then the amplitude's invariant. But if we take two identical fermions and swap them, we get a minus sign. That's all I mean. Again, something that's usually automatic, but for us, we want as an input. Okay. Lorentz invariance. Essentially, all this is a statement that our kinematic variables should depend on, let's say, 4 vectors or spin or helicity variables, which I'll get to in a second. But otherwise, it's really just a specification of the kinematic variables. And last but not least, factorization. Okay, this is the most. All these other ones are kind of really low level. Factorization is the one with the power. Okay, let me tell you what I mean by it. If you like, factorization is, and I should have said this before, I'm going to restrict almost entirely to tree level, again, just because this is an introduction to amplitudes. We're going to start at tree. Factorization we can think of as the tree level avatar of unitarity. What precisely do I mean by that? Well, the statement is that if I look at a higher point amplitude and I tune external kinematics, so let's say I took a 4-point amplitude. This was some 4-point amplitude, a 4-point tree amplitude. The statement of factorization is that if I take this and let me write out what I'm going to do and then explain it. It's just a statement as a kinematic function. Okay? So A4 as an actual function. If I multiply by s minus m squared and then send s goes to m squared, well, if this has no poles in s minus m squared, then of course I'll get 0. Okay? But if it does have poles in s minus m squared, then I'll extract that residue, much like we saw in Eugene's talk a bit ago. And what we end up getting is the product of 3-point amplitudes between those objects. Okay. Now, this, of course, looks a lot like Feynman diagrams. It looks like I'm saying to build 4-point, take two 3-point vertices and glue them together. Okay? But that's not the direction of how this equation should be thought of. I'm not just taking Feynman rules and going this way. The point is instead that I'm starting with a 4-point ansatz. So this A4 is some soup of Mandelstam invariants for which I have many free coefficients that have been unfixed. And the point is when I go to these very special kinematics, where this thing's on resonance, whatever I get from the residue is the product of 3-point amplitudes. Okay, so if you like, in this procedure, I don't have to talk about off-shell quantities. I've gone on shell, I've turned the intermediate leg on shell. The reason why this is the most powerful constraint is simply because it lets me relate lower point, 3-point amplitudes to 4-point amplitudes. So essentially our procedure is we're going to construct all 3 particle amplitudes because 3 particle amplitudes will be fixed by Lorentz invariance. Okay, so even that alone is a little non-trivial and maybe a little unintuitive. We're used to thinking of the propagators as Lorentz invariant, but 3-point should be, dynamics, okay? But no, 3-point, even though we think of it as dynamics, interaction, so to speak, is secretly all still fixed by Lorentz invariance. those, once we have those, we'll feed them into this kind of constraint to get higher point. Okay? And we'll do that hypermechanically. Okay, good. Any questions about that? Yes.
It is often advocated that the advertise that the amplitude method does not rely on Lagrange formulation.
Yes.
And you list some of the physical principles there.
Right.
For example, exchange symmetry. Can you talk about that?
Without a Lagrangian. Oh, that's a good question. Yeah, so So if I didn't have exchange symmetry as an input assumption, could I try to derive it through consistency? Well, it's an assumption, so in some sense, I'm just accepting that I take it as input. But I think maybe in some circumstances you could try to derive things like CPT, spin statistics theorem, but actually I'm not sure if there's a general argument. So I haven't thought about that actually, so I don't know. I will say the general idea that I have to like throw the Lagrangian away, make my life as hard as possible and never assume anything but what I need, I don't need to be that much of a hardliner because I'm not trying to be a constructive field theorist. So I'm not trying to like literally with no residual information at all from Lagrangians. I still will just use that because I find it helpful. But this is really just trying to illustrate this is how someone who's more or less unmoored from Lagrangians would build these objects. But I don't need to be so hardline to say that I'm going to prove, I can prove every possible splitability. Like, I'm not going to prove a general algebraic quantum field theoretic axioms this way. That's not going to happen. I have to assume something. Okay, good. All right, so let me now get to some actual real equations. Okay, and the kind of proper way to do this bootstrap is really with spinor helicity, but I kind of like to, at least recently, describe things in general dimension, just to maybe convey that the bootstrap approach is not necessarily restricted to 4D. So I want to tell you about a bootstrap for, let's say, Yang-Mills and gravity for these low point amplitudes, which we can frame in terms of these polarizations and these momenta. Okay, so these E's and these P's. Okay, so this is going to be my introduction to the notion of a minimal kinematic basis. The idea here is that we want to bootstrap amplitudes, so we have to know what variables the amplitude depends on, but we need to make sure the variables are not redundant. Okay, what do I mean by not redundant? Well, if I just had momentum, pi mu, and let's say ei mu. Okay, so we had polarizations and momenta. So this is momentum of leg I. And I have polarization of leg I. Okay, there's already these chosen to be arbitrary d-dimensional vectors is not going to be on shell. I need to impose momentum conservation together with on shell conditions. Okay. So what that means is, let's say if I have massless particles, I should set pi squared equals to 0. Let's say I had massless gauge bosons. Okay. We know that polarizations have too much information, too many polarizations, more than the number of physical polarizations. So we have things like this transverse condition. And we could even, if you like, and this is like a luxury, choose polarizations that are like helicity basis like so that E squared equals 0. Okay, this is really an option that you could have or not have. But typically if we had a Feynman diagram expression, which we're going to slowly march away from, we'd impose these kinds of conditions. But this is not even sufficient yet. Why is it not sufficient? So if I just like in an expression like this surgically set these identities to be true, I'd kill a bunch of terms, but I would still have a redundancy. The reason why is that I need to impose momentum conservation. So I need to have the sum of I equals 0. Okay. So in other words, what I should really do is take one of the momenta and just eliminate it completely. So take the very last leg. If I have an n-point amplitude, take Pn and eliminate it with this on-shell condition. So if you do that, all of a sudden Pn is gone. Okay? And then you might think that you're in a minimal kinematic basis. But here you're still not in a minimal kinematic basis because, so in other words, you can eliminate Pn, right? But you still have other identities you have to impose because Pn squared equals 0. Okay? Pn is also on shell. So after you eliminated Pn, you were actually writing it in terms of all the other momenta. So let me just write it this way. This is P1 plus P2 all the way to Pn minus 1. Okay, so the on-shell condition for n is actually some nonlinear, some constraint on P1 to Pn minus 1. Okay? And similarly for Pn dot En equals 0. Okay, so in other words, this constraint is saying that minus P1 plus P2 all the way to Pn minus 1, En is 0. So this is just a constraint on the other momenta. Okay. What we want to do when we design a minimal kinematic basis is essentially remove, if you like, mandate all of these equations are true by eliminating Mandelstam invariance with these equations. Okay? So in other words, we can think of the full space of off-shell kinematics as all the Mandelstam invariant that you can build from E and P. And so at least naively, you would have said there's Pi dot Pj, there's Pi dot Ej, and there's Ei dot Ej. Okay, you just write every combination. But I can think of these variables. So if I think of each of these Lorentz invariant variables as its own independent variable, they're not independent because of these constraints. Okay? So what we can do is impose these constraints, these linear constraints on the Mandelstams by simply eliminating whichever Mandelstam we want. Okay? So the way we get a minimal kinematic basis is to essentially take all the on-shell conditions and use them to solve and eliminate for some number of these inner products. Okay? So let me not bore you with that explicit counting and exercise, but I'll just show you what does three-particle minimal kinematics look like. So three-particle minimal kinematics. Okay? So what I just mean is, what are the variables, the on-shell variables that the three-point amplitude can depend on? Well, it can depend on E1, E2, E2, E3, and E3, E1. Crucially, these inner products of polarizations can never be solved for on these conditions, and these conditions don't depend on them. So these are all independent in general dimension. Then we have P1. I'm just making a choice here. Okay. P2, E1. Okay. There's 6 variables that this thing can depend on. And again, I've kind of made a choice of which P dot E's to include and which not to include. Let me unpack this slightly more. You might ask, what about the ones that are missing? What happened to P1 dot P2? Where did that go? Well, again, using the on-shell condition and momentum conservation and like what we saw before, at 3 particles, P1 dot P2 can be written as P1 squared, P2 squared, P3 squared, so it's 0. So we don't include it. We don't have to include 0 in our basis. So kind of crucially at 3-point, P dot P is not something the amplitude can depend on. A corollary to that is that if you have let me not jump ahead. But the point is there's no P dot P's in this basis. Literally, there's no physical process that can depend on it because these are all 0. You might wonder about other choices I could have added here, like, well, let's say, what happened to, let's say, P3 dot E1? Okay, where did that guy go? Well, here you can use identities like replacing P3 with P1 plus P2, in which case this becomes minus P2 E1, okay? Because P1 dot E1 is 0. So that's P2 E1, which is already in the basis. Okay? So that's why things like this are also not included. They've already been introduced through other pieces. So the point here is that this is a minimal basis for objects at 3-point. We can write down an analogous basis at 4-point, which just has more and more of these E.E's and P.E's. And, oh good, I still have time. So I still have 25 minutes, right? I'm doing, yeah, good. I think.
About 30 minutes.
30 minutes, perfect. Okay, awesome. Good. So in fact, let me, for that reason, actually write down the 4-point basis just so that I can be concrete, because we're going to do 3-point and 4-point. Well, actually, let me not just, yeah, let me refrain from that just because it's a lot of text. Let's think about 3-point. Okay. Okay. So let's talk about scalar theory bootstrap. So this will be relatively simple. What's the point here? We're going to use the principles of Lorentz invariance, dimensional analysis, exchange symmetry, and factorization to bootstrap every scalar theory up to 4-point. Okay, that's the plan. How do we do that? Okay, so let's start from 3-point. So 3-particle scattering of scalars. So okay, so 3 scalars come in at a vertex. Okay, but we're not going to use Lagrangian. I'm just going to say, well, these are the kinematic functions it can depend on. It's a scalar, so it has no polarization, so it doesn't have E. Okay, so it can't depend on these. So the only thing it can be is a constant. A constant, which is lambda, which I'll call lambda, constant lambda. So I'm saying that the only 3-particle scattering amplitude of scalars is a constant, otherwise known as, if you like, a potential V of phi, which is phi cubed theory. Okay? Now immediately, I mean, if you know anything about EFT or QFT, you should be worried. Wait a minute, aren't I missing something? Surely I can write another vertex that isn't phi cubed if I just throw down derivatives. Okay? What happened to d phi squared times phi and so on? Okay? Well, this comes back to the example of the scalar we saw before. Okay, so the counterpoint would be, wait a minute, this can't be right. What happened to d phi squared times phi? There's a 3-point coupling, it's got 2 derivatives. This would show up in an EFT nominally. Yeah, where did this thing come from? Or where did this thing go? Okay. The claim here is that this object is actually secretly trivial. Right? You can already anticipate that it's going to be trivial because it showed up in the previous example I had. In the previous example with d phi squared times g of phi, this is just one of those terms, so you can anticipate that it's going to be trivial. But let's see hyper explicitly why it's trivial. Okay? So I can take this object and I can rewrite it just by integrating by parts. So 1/2 box phi squared minus phi box phi, which is minus 1/2 phi squared box phi. Okay, so in other words, I can just literally by integrating by parts momenta, rewrite this object as a cubic interaction that involves a single box acting on a phi. Okay. Now, what does that imply? Well, when certainly those who have seen EFTs and worked with the standard model EFT SMEFT or in gravity, they know there's this common mantra that you can plug in equations of motion to get equivalent theories. Okay, sometimes we'll hear it in that incomplete way, which is that like I can freely plug in on-shell equations of motion and get equivalent physics. And I remember as a student hearing that and being puzzled because, wait a minute, the Lagrangian's off-shell. Since when do I get to plug in an on-shell statement like the equation of motion into an off-shell object and get something sensible? Well, the point is that when one writes down an equation of motion or inserts the equations of motion into an action, it's actually the same as a field redefinition. Okay, let me just parenthetically tell you why that's true if you haven't seen the story. Okay. It's not in my notes, but right, if I took phi and I sent it to phi goes to phi plus d phi, okay, where this is some smaller than phi by some power counting. let's say some higher dimension operator coefficient, some scale, some cutoff scale, then this would send the action to action goes to action plus delta phi times the equation of motion, because that's what the Euler-Lagrange construction does. It says when you vary phi, you get delta phi times EOM. So when we plug in an equation of motion into the Lagrangian, we're secretly plugging in equation of motion times delta phi, and we're doing a field redefinition. Okay, so field redefinitions are the same as plugging in equations of motion. What that means is I can find some transformation phi goes to delta phi plus delta phi that eliminates this. Okay, very concretely in this example, if delta phi was 1/2 phi squared, I'm going to have some sign off perhaps, but if this is 1/2 phi squared, then I get 1/2 phi squared times the equation of motion, and then I could eliminate the term. Now, operationally, it means that this 3-point amplitude does not affect, this 3-point vertex does not affect the 3-point amplitude. Okay, so for the uninitiated, that could sound confusing because you often think of interaction vertices and amplitudes as the same. But the point is that this is a vertex which is proportional to box of one of the external legs. So if you drew this in a diagram, that box would hit this external leg, and that external leg's on shell. Okay. Now you'd be tempted to say, okay, this is 0, I just cross it out, it's all 0. You may be a little confused how you added something and it disappeared. But the point is, the equation of motion generally will be box phi equals other stuff, like, I don't know, phi to the 4 and other interactions in play. So there's a right-hand side to this. What it means is that this box phi actually connects with whatever other interactions exist in the theory. And this box cancels the 1 on box from the propagator to give you effectively a local term. And so in this kind of toy example, it looked like I was writing a 3-point amplitude, but secretly I was writing a 3-point vertex, which pinches a propagator and really gives me a higher point vertex, 5-point in this example. Okay? So in other words, the physics didn't disappear. It just was consistent with there not being a 3-point amplitude that's not a potential. Okay? So we here stand by the statement. There is no 3-particle scattering amplitude in any EFT for scalars. Does not exist. You can also add masses. It won't change the conclusion. It's always going to be just a constant. Anything that you try to write is secretly 4-point, 5-point, 6-point, or higher. Okay? Some higher point vertex. Okay. This is, in the language of SMEF, this is what people say when they go between operator bases. When they plug in equations of motion to remove one term and get another, this is precisely what they're doing. Okay. Maybe I'll leave this as an exercise, but this statement is true irrespective of whether these are the same scalar. Yeah, I'll leave this as an exercise. Oh, I should have erased that. Oh, well. But that's fine. Let me just say it in words. If these 3 scalars were different flavors, let's say there were 3 different scalars with different masses, I still can't write down P1.P2. Or at least if I did, it would always become a constant. So for 3 distinguishable scalars, not massless, all with different masses, it's still a constant. What that means, and I'll just leave this as an exercise, is that even an amplitude, a vertex that looks like this, d phi 1, d phi 2, phi 3, okay, 3 distinct objects, this is also can be eliminated with equations of motion. This is also, there's no 3-point amplitude in this. Okay? Okay, good. Any questions about that? All right. So that explains like the simplest possible 0 that we found before, which was 3-point. Let's move on to 4-point. Okay, so 3-point was easy. The only 3-point amplitude is a constant. 4-point is essentially as easy. In fact, let me just erase this. 4-point's essentially as easy. So for 4-point, again, I'm trying to illustrate in this most basic example how we think about amplitudes and bootstrapping. So to build 4-point, it's slightly more complicated because A4 could depend on, let's say, S, T, and U. Okay, it could depend on lots of S and T, let's say. But it'd be convenient to split A4 into two types of pieces, which I'll call factorization and contact. Okay, and this is just fancy language for the following statement here, which is, let me put it this way. The factorization piece is the piece that has any pole in S. So any like 1 on S or 1 on T, okay, anything with a denominator is in this factorization piece. Meanwhile, everything in contact, this is what it sounds like, has no momentum-dependent denominator. So this is just like a polynomial in S and T, S and U. That's redundant, but it's a polynomial in the Mandel stems. While this one could have poles. Yeah, so I'm doing a very coarse-grained split between them. I'm not saying it's unique, but I'm just saying imagine that all the singular pieces are actually only in this piece. Okay. The reason why those singular pieces have to do with factorization is kind of what I said, it's been erased now, which is factorization is a statement that I can hit that pole, extract the residue, and that residue will give me lower point amplitudes. Okay. So without loss of generality, let me write down a factorization. I can write it as ns over s, t over t plus n over u. Okay, so here I'm imagining, I should have said, in any case, if you're assuming factorization and you're building a bootstrap like this, you have to tell me what your spectrum is, right? Because no one gave you a Lagrangian. Even when you write a Lagrangian, someone tells you the spectrum. Just like that here, I need to be told what the spectrum is, and I'm assuming massless particles, okay? Which means that the only poles I'll get is 1 on S, 1 on T, and 1 on U. Now, this factorization piece could have pieces that aren't singular, like NS could go as S, NT could go as T, and U could go as U. But I want to account for any possible singularity, so I'm just going to write it this way. Okay, so this is just a way of parameterizing all those pieces. Okay. Now, when we impose factorization, we find a relationship between higher point and lower point. Okay, so the kind of point here, the way to think about this is, at 4 point, we assume nothing except that the amplitude has pieces that are non-analytic in momentum, that is to say, simple poles in momentum, and then pieces that don't, okay, everything else. We've assumed very mild assumptions here. And now we're going to impose factorization to determine what end factorization is. Okay. So concretely, if I take the limit as s goes to 0 of s times A4 factorization, okay, this is simply the factorization condition I wrote before, which is extract the residue on the s goes to 0 pole. This should equal minus A3, A3. This is the formula I wrote before. And this is a constraint I want to impose. What that means is, just plug in for A factorization here. We get the limit as s goes to 0 of ns equals minus lambda squared. Okay, in other words, we just pluck out the 1 on s pole. Okay, that kills off the 1 on t pole because it's not singular in s. This has a pole at s plus t, but we're extracting the residue at s equals 0, so this also is not something we worry about. So what we're left with is s goes to 0 here. S goes to 0, and this is the constraint. This tells me that ns as s goes to 0 is minus lambda squared. So that fixes the residue at that point. By crossing, this then implies that we can choose, by permutation invariance, ns is lambda minus lambda squared, and that's the same as nt, and that's the same as nu. All the same. Okay, so we've solved for this part of the ansatz. Now you might worry, what about the pieces that got thrown out? What if ns was proportional to s to the 15th power, right? That could just be a piece here that vanished. Well, any such piece can be accommodated for by the contact term. Okay, so this is kind of always a regular thing that happens, which is when we fix singular terms, we're really fixing the residue, but everything subleading to that residue is secretly part of the contact piece, which is not yet fixed. So I've not fixed that. It's still inside this unfixed A4. It's just restating the general feature that factorization fixes residues on singularities. If you don't have a singularity there, it's unfixed. That unfixed nature is a coupling constant, and it's free. If you want to fix that coupling constant, you need some other principle or some reason to fix it, which would be another bootstrap principle. Okay, so that's often the kind of picture. Lower point fixes everything that has a pole in it. Everything without a pole, we need a reason to fix it to whatever value it takes. Okay, so in the end, we get the factorization is just minus lambda squared, 1 on S plus 1 on T plus 1 on U. Good. And then it now just becomes a question of the factors, the contact piece, which is the easy part, the even easier part. No, this is too hard, but that's the even easier part. And to get the 4-point contact piece, we literally just enumerate polynomials. Because as I said, we're talking about functions that have no pole, no singularities. So for A4 contact, it means that we just have to enumerate all possible functions that are polynomials in S, T, and U, which, since we assumed here this was a single scalar, that are permutation invariant with respect to S, T, and U. So that's pretty easy. Well, it could be 1. Okay. So these are different options. It could be 1. It could be S plus T plus U, which is 0. Okay. I'm going to stop writing this. It could be S squared plus T squared plus U squared. It could be S cubed plus T cubed plus U cubed, which is also 3 times STU. Okay, so there's like you just keep going. You just keep literally enumerating higher and higher degree polynomials, but these all have names. Okay. This 1, which just means by 1 I don't mean literally the number 1. I just mean a constant dependence. This is just phi-4 theory. Okay, so this is phi-4 contact term. This 2 derivative case we already encountered. Okay, this was a 4-point amplitude that has 2 derivatives in it. That's why it goes as linear in S, linear in T, and linear in U. The only invariant you can write that's permutation invariant is the sum, which is 0. That was precisely d phi squared times phi squared, which again we saw before in that that scalar model should have a vanishing S matrix. So here we've learned why the 4-point amplitude vanished. S plus T plus U is 0. Okay. So the amplitude's way of understanding why that theory was secretly free is that you can't write a 3-point amplitude, and at 4-point amplitude is 0. These other ones are physical theories. Okay, so this here is d phi to the 4th. This here is d phi squared times d phi squared, and so on and so forth. Okay, so it's as obvious you could just keep enumerating things. This is even a way of enumerating all the higher dimension operators in the theories. Some folks have decided to try to do that, again, for SMEFT or in general for EFTs. But simply enumerating kinematics is the same as enumerating vertices. The number of independent objects will be precisely the same. Okay, any questions about that? Yes?
How do we know from principles that the 4 there only at 1?
That's only a simple pole. Yeah, very good. So good. So you could ask, why don't I have higher order poles? Like, I don't know, like 1 on S times 1 on T. I should have mentioned this before, but when we have, let's say, 1 on S times 1 on T, or let's say 1 on S squared, these are non-local poles because in the following sense. So let's say, imagine we had this, 1 on S times 1 on T. If you went to the 1 on S pole, we get that the product of 3-point amplitudes goes as 1 on T. But the 3-point amplitude should be local, which means it should only have momentum dependence in the upstairs. If I said A3 times A3 equals 1 on T, that means that the 3-point vertex has like an inverse momentum, which is a no-no also for the interaction. So as you can see, the only 3-point amplitude is constant anyway. So you can't have inverse powers of momenta in your 3-particle coupling. So that's why things like this would be illegal. Things like 1 on s squared, okay, this illegal depending on your perspective. If your asymptotic states satisfy a dispersion relation, which is box phi, then you'll never get double poles like this. Again, for the same reason. It'd be like, it would tell you that the 3-point amplitude squared is 1 on s, which doesn't make any sense. It would be singular. But, of course, there exists some times when you might be interested in more exotic theories. Let's say, like conformal gravity. In conformal gravity, you do away with the Einstein-Hilbert term. You just start with Weyl squared or some curvature squared invariant. And it naturally has 4 derivatives in its kinetic term. And then you could bootstrap that. Of course, those aren't unitary. Those have all these issues. But it's up to you to decide your principles. If you decide that's OK for you, then you could bootstrap things with double poles. It just reflects a different dispersion relation for your external states. You could do this super generally. If I was in a non-relativistic theory, I could put a non-relativistic kinetic term here. If I was Navier-Stokes, I could put the quadratic heat equation here. I could do anything I want. The point is, if you have some limit about what you're expanding, the dispersion relation is what dictates this propagator structure. Yeah. Any other questions? OK, good. So yes, yeah.
In the last point here, you have a usual Lagrangian fixed series function of phi and del phi.
Right.
Not secondary.
Yes.
So you allow this one.
Yes. So again, same statements here about ghosts. So normally, if you have higher derivatives, you couldn't define necessarily a Hamiltonian evolution. You'd have Ashkenazi ghosts, all that usual statements of issues. There exist theories where all those ghosts cancel. So famously in, say, like Galilean type theories, despite the fact that there's many derivatives here, the equations of motion are still the regular second order differential equation. So you don't have to introduce additional input in the initial value problem. But it's up to you. So if that bothers you, then you should assume a structure here that doesn't have Ashkenazi ghosts, which exist. If you're OK with it, you can include it. But it's, again, up to the assumptions you make. What we'll find is that in amplitudes, in terms of the hidden structure, kind of amusingly, the theory that shows up when we talk about these kinds of higher derivative pieces happen to be free from these Ashkenazi ghosts. Like, for whatever reason, amplitude structures like to exorcise them, and they are gone. I don't know what to make of that. They have other pathologies other than those ghosts. But indeed, in general, such a thing would be considered pathologic, for sure. Unless you have a whole tower. Of course, you have an infinite tower, and this is an EFT from integrand heavy state. You can get states like this. But in of itself, it would nominally introduce ghosty particles. It's up to you whether you want to include them or not include them. OK. In my last 3 minutes here, let me now jump from 4-point to n-point. Again, in returning to this kind of story that I started with, which was that 2-derivative theory. Okay? So the theory with 2 derivatives on the scalar field. So again, just to remind you, it was some integral d phi squared times g of phi. Okay? So I'm now going to show you, again, just to see how this is the kind of MO of amplitudes, folks. Rather than be clever and find the field redefinition, let's show from amplitudes that this S matrix is at 0. Like not just calculating kind of stupidly, but what's the amplitudes argument, the inductive argument that tells us that this thing is trivial. Okay? Well, given what we said about factorization pieces and contact pieces, we can prove this by induction. Okay? How do I do that? Well, first we compute the base case, A3, which you could just do by hand. Okay, you could literally compute it, which we did, and you find that it's 0. Okay. We also computed A4. Okay, we did the A4 case also. Okay, let me be a little more concrete here. So we have a factorization piece. We have a contact piece. The factorization piece is proportional to 3 points squared, but that's 0. So this is 0. Okay. The contact piece I just talked about, it's s plus t plus d equals 0. So that's also 0. So this was 0. Okay. But you can see how the induction argument is going to work. At every higher point, there's a factorization piece that depends on every lower point. But I've already showed you that all the lower point pieces are 0. So maybe more explicitly, if I was at 5 points, there would be a 5-point factorization piece. And this just means anything that is non-local in P1.P2 and P4.P5, the two propagators in play, just anything non-local. And then a contact piece, this is contact. But this factorization piece's residues can only depend on A4 and A3, which are both 0. So this is also 0. Okay? Which means I just have to enumerate all possible contact terms with 2 derivatives. Now in general grounds, I want to write down some AN. It's got to be something with 2 derivatives, so it has to be PI and PJ. And it has to be permutation invariant, so it has to be summed on I and J. And this thing is 0. Okay, you can show also that it can be expressed as the sum of total momentum squared. So the endpoint contact term is vanishing. So that completes the argument. If you like, it's in some sense requires you not to know about field redefinitions or anything clever. It just shows you that if everything has no singularities, because everything at lower point was 0, and I can't write down a contact term for it, then it's 0 also, and then you apply induction. So this then establishes that the full S matrix for this thing is vanishing. That's the kind of flavor of argument we like to make, which is we look at the factorization pieces, we look at the contact pieces, and then we make broader arguments. Okay, I think probably I'll stop there. But the plan for the next lecture is we're going to do vectors and tensors. We're going to do gauge theory and gravity through this kind of picture. And kind of a nice output of it is that we're going to already see some of the structure I mentioned. So already in this kind of really basic bootstrap, we're going to see double copy linkages between theories that normally would seem quite disparate. And then I think maybe after that, I'll decide whether I'm going to do spinor helicity or just jump right to maybe more advanced things. But maybe that's a good place to stop, and I can happy to take more questions. Thanks. Sure.
In the early stage of your lecture, you mentioned about vanishing amplitude if LP is not maximally modulated.
Yes.
Yeah. So
I thought such a vanishing amplitude is only for the Yang-Mills theory, isn't
Yes.
it?
Yes, that's right.
Is it correct?
Yes,
then
that's right.
then if we consider another theory, then such a non-maximally violating amplitude also alive?
Yes. So in fact, we'll talk about that in the next lecture. In fact, even Yang-Mills, but with some other corrections to the leading piece. So indeed, once you include loops, higher dimension operators, more complications, the types of vertices you have will change, and then a different outcome will occur. So in fact, we'll discuss literally the types of operators that will have 3 minuses or 3 pluses in the next sequence, actually.
I see.
So we'll
Thank
talk
you.
about that.
Yeah, thank you. Yeah.
Sure. Yes.
You did some path integral arguments for the field redefinition.
Mm-hmm.
And I wonder that if there is any contribution from path integral measure when you do the...
Yes, for sure. So if you want to do this correctly with, at loop order, then you'd include the Jacobian. Of course, that's even how we could compute the anomaly for the chiral anomaly. What's nice, though, is that if you do local field redefinitions, so in principle, you can do very complicated field redefinitions. But let's say you just did phi shifts by phi to the n. I think at least in regulating with dim reg, you can show mechanically that since there's no singularities in that Jacobian, it's trivial. But for non-local field redefinitions, like let's say 1 on box phi to the n, you would have to care about it and would contribute to physics. So indeed, just like in any integral, you better treat it carefully, and if you don't treat it carefully, you get everything wrong. But of course, once you treat it carefully, you get the right answer. Yeah.
Thanks.
So you should treat it carefully. Yeah. Sure.
So here, your example was for single real scalar field, right?
Yes, that's right.
So suppose you consider, for example, SO3 global symmetry
Yes.
with three-dimensional
Right.
three-dimensional vector, internal vector,
Yes.
and so del phi vector scale and G
Very good.
phi dot
Yes.
phi vector dot phi vector. In that case,
The answer changes.
the
So
same.
it
or
was
not?
the crucial element that let me zero these out was permutation invariance, which told me that there's no label other than momenta. So if I swap two legs, that's equivalent to swapping their momenta because there's no other label. If you instead made these flavored, like in the Carroll-Lagrangian, okay, then there's IJ indices. This is a field space metric. You don't get zero precisely because swapping external states means also changing the flavor label. So in other words, there is attached to any of these terms, I don't need full permutation invariance because there's a coupling constant like lambda A, B, C, D, which also flips together with momenta. And that small loophole is the loophole that the Carroll-Lagrangian slides through, because the Carroll-Lagrangian is, of course, a two-derivative scalar field. It's not vanishing, but you can precisely, if you like, bootstrap it from these same principles.
Okay, so a little bit, somewhat related question is that one important scalar field in nature is a Goldstone boson.
Right.
So, which has only derivative coupling,
Right,
So
right.
in this kind of argument, what is the difference between Goldstone boson scalar
Great question.
and
Right.
ordinary scalar?
Very good. So everything is based on your assumptions. If you only assume Lorentz invariance and factorization, the output of your bootstrap would include Goldstone bosons and non-Goldstone bosons. All of them would be together. Potentials together with derivative coupling. If you want to add Goldstone bosons, there's actually work that I did with Josh Shen and others. You need another input assumption, which is to say, you have to ask, what is the S matrix avatar of spontaneous symmetry breaking? And that turns out to be the Adler zero. So the famous Adler zero says that if I take a Carroll-Lagrangian amplitude and I take one of its external momenta and I send it to zero, then actually the amplitude scales as some positive power of p. Usually p to the 1. It scales as p. So as p goes to 0, the probability goes to 0. This is not Lorentz invariance, or I mean, it's none of the assumptions I made. It's an additional assumption. What's kind of cool is that if you impose this as a constraint, you can uniquely fix the Carroll-Lagrangian structure. Or if you start adding more derivatives, you can get Born-Infeld, Galileans, all these kind of derivatively coupled scalar theories that show up in HEP PH. A large fraction of them come from this principle of demanding vanishing with some degree. So again, there's no free lunch. You want to get the Carroll-Lagrangian, you better assume something effectively physically equivalent to spontaneous symmetry breaking, which in this case is the soft theorem, the Adler zero. So you can bootstrap tons of theories this way. You can build a map of EFT space. But it turns out that, yeah, that symmetry breaking is a different kinematical assumption that you just impose.
So
Yeah.
then, in the Lagrangian field theory case, the exact Goldstone boson still has some mass scale where
Yes.
symmetry is broken.
Right.
So in this approach,
Very good.
How does it appear?
So here, this is the chiral limit of NLSM. If you wanted to add, say, the chiral symmetry breaking mass in the actual Carroll-Lagrangian, it would mean that you want to write down amplitudes that involve 1, 2, or 3 insertions of a chiral symmetry breaking parameter. So it would be some correction to this, which scales as a constant, which would be the m up.
I'm asking
Yeah.
about I'm not talking about the M, but the V. For example, when you have this potential, basically.
Oh, you mean like an axion potential?
Yeah, yeah.
Oh, good. I see. Separate question. So not chiral symmetry breaking from not explicit chiral symmetry breaking, but chiral symmetry breaking from the QCD condensate. That so that would be much more difficult to get from an amplitude's point of view if you wanted the QCD side, because the QCD side is strongly coupled, right? But okay, I don't know anyone who's actually asked this question, but let me try to answer it on the fly. So for let's say an axion potential, there is still, of course, a symmetry that it has, which is the discrete ZN symmetry. So in principle, that actually, not in principle, that implies a set of selection rules on amplitudes, since they must be invariant under some discrete Ward identity under which they shifted. And I don't know anyone who's actually studied that, but I think it might be cool to try to build the potential that way. There is a history of building potentials based on constraints from amplitudes. Like you can build sine Gordon through a kind of in a different way. You can build sine Gordon from a constraint on no scattering. Maybe something like this could also be built from selection rules on higher point. But I don't know anyone who's tried building the non-perturbative axion potential, say, from amplitudes. That might be, I'd have to think about how easy that would be. But whatever it is, it would have to care about arbitrarily high endpoint amplitudes. Everything I've said here is at A3, A4, low point. But of course, the cosine potential needs to know about arbitrarily high point, like phi to the infinity. So that's why it naturally is not something that amplitudes folks would look at. But in principle, we could ask the question, at infinite numbers of particle scattering, what constraint does a periodic discrete shift symmetry impose on scattering? And again, maybe someone in the audience has thought about it, but I personally have not. But it could be cool to try to figure that out.
Any other question? Last time to speak again. Everybody.